what we have studied last time, in the beginning, very beginning, we talk about the curvature. So the curvature over is R radius over any curvature. So 1 over R, sometimes people is written 1 over 1 over rho is kappa. This is curvature of line. And in relativity, so this is just a little bit small portion of relativity lah you belajar. So kalau ada space time that is warp, maybe this one can only warp because due to some gravity, some mass. So let's say there is mass here, but of course you don't need to know the full portion of it. You don't need to know that. You have to go into my class. And so this line, this is the curvature of line. Okay, you learn this thing already. One, if you remember, this one is something like acceleration dv dt plus k and v squared is equal to acceleration, overall acceleration. So this one is something like this. If there is a line, this is space-time line. Space-time line is giving curvature. This curvature of space-time line is given by what we call given by second first kind of the second kind of this is Christopher symbol for it, but and this is what we call the curvature of space-time line. Line of space-time. Because every point of this is space and time, x mu. X mu means in tensor, we have x0, x1, x2, x3. So x mu means t, this one means r, is in spherical coordinate, this one in theta, this one means c. So mu means mu or any indices means 0, 1, 2, 3. So this is space for spatial and this is for time. Okay. And there is another one is something like this. Same thing like this. Curvature, and this one. But this one is not line, not just line. It's not just line. It is because of some mass that walk this time. This mass, this just mass walk. This has nothing to do with mass, just curvature. But this part of this is like a portion of area on the portion of area on the that is curved, area that is curved, portion of area that is curved. It's patches of area. Patch of space-time surface. Patch of space-time surface, and this is space-time surface, all these, and they have curvature. What we call curvature of space-time surface is curvature of space space-time surface. Okay. This is what we call the Riemann tensor. Something like what we call, let's say, something like theta mu. This one is alpha. So this one is something like the x mu d tau plus mu lambda vector dx lambda dx vector tau is zero because this is equation equal. But this is velocity square, this is acceleration, just like this. Just like this. But this is more like more like just a line. Just a line on this 3D space. In this 3D space. So this is space-time line, and this is the space-time surface. Okay, space-time surface. So space-time surface is something like something like that. This is equal to zero. This is also a curvature. The pattern of equation is similar to the curvature. So this talking about space-time curvature. This is what is called a Riemann tensor. So today we going to just put some calculation of Riemann tensor. Because it's not difficult. It's just the calculation by using tensor technique. Easy. So this is we call Riemann tensor. Okay. And if we contract, like for example, if we contract the Riemann tensor, that means we contract mu is equal to beta. Okay. So this is when case mu this one alpha is equal to beta. We contract it. It becomes something. It can cancel out. It becomes R mu D. We call it Ricci tensor. It's the same thing. But Ricci tensor later, if you learn the generative with me, you can calculate. You can calculate what the most famous equation, the Einstein tensor. Okay, that's why today we just want to show by using just tensor technique we can calculate Riemann tensor, we can calculate Ricci tensor. Okay. Hopefully we have time, but I just give you maybe, and then you can try to do yourself. This one you all have notes, right? And you don't read. This one have you tried? Okay, it's very easy. Take 1 over 2 lambda r, and then you differentiate this one. Differentiate d is lambda r with respect to r. This is lambda is a function of r, so it means you differentiate by using chain rule. You use this r, and then the lambda r and dr. So you have 1 over 2e lambda, and then when this one differentiate, you've got the same thing. You have to refresh your calculus, and then you have this one. You got d lambda r over r. So this one you can okay. Okay, so you have e lambda r become e lambda R with respect to E lambda R, and then we lambda R. So we will have half lambda R. What's the I? Okay, never mind. Okay. This one because because I take a lambda, but something else in some other note they have two. Never mind. Okay, now we quick one. This one quick one. Very easy. This one. Okay, I record ready. This one, I think you already last lecture. Okay, so we come to this. So you just differentiate. So I do the again. The differentiation very easy. So we have this conclusion of this. One is equal to negative 1 over 2e lambda r, and then you differentiate e lambda r with respect to r. Problem is respect to r here, but this one is lambda r. So just negative 1 over 2e lambda r, and then this one very easy, just using case rule. You with respect to lambda r, the r and then lambda r, then r. So we have negative 1 over 2e lambda r, and then respect just lambda, let's say lambda r, you say x, ex, lambda r is x, remember, x, so ex, differentiate with e lambda r with x, you got ex, is calculus, so you got the same thing, e lambda r, then this is e lambda r, so you have, then so this one, you have 1 over 2 e lambda r, dekat sini je. That's it. This one is enough. But sometimes people, of course, di lambda r is symbolized as lambda prime. They symbolize it. Kalau differentiate with t, kalau is also a function of t, so it becomes lambda dot some but until this should be okay. Okay, now we go for the reach tensor. Okay, so far okay. Right? Okay, alright. Mana? This one. Oh, negative. This one. Oh, so negative, negative. This one negative. So positive actually. Positive. Because okay, why? Okay, this one is negative also. This one is G. This one is G. So it's G. I mean G11. G11, right? G11 is E lambda R, and so G is negative, right? Negative. So G11 is 1 over G11, negative 1 over E lambda R. Okay. This halfway from the formula of the Christopher symbol I showed you last week. This one, I think this one here. Okay. Now, let's go little by little of this. Maybe tak sempat but you can figure out on Google. But if you cannot figure out, we come to sini. Okay. Now, let's say Riemann tensor, called Riemann tensor, is alpha. We want to get the Ricci tensor as this one. This is Ricci tensor. This is Ricci tensor. So is a Riemann tensor general Riemann tensor. General Riemann tensor is, let's say mu is say beta, is alpha here, is nu. So all alpha, beta, mu, all is just 0, 1, 2, 3, time and space. Okay, just indices of that. So you don't need to know how to write this thing, but I just give you this shit. It has pattern, some pattern. Out the pattern over so if we contract alpha is equal to b, alpha is equal to beta, so we have Ricci tensor. Okay? R alpha u jadi alpha ini mu. So this is contraction. I showed you last week. Contraction. So it become R mu u. Ini rank tensor of rank 1, 2, 3, 4. 1, 2, 3, 4. Tensor 4 become tensor 2. So now alpha is beta, so we just write it down alpha. So this one also alpha, and then alpha. This one alpha x and then this one sigma mu alpha minus sigma mu alpha sigma mu. So why I can write this way, because alpha is beta, so every beta is beta, we change to alpha. So you got this. This is a Ricci tensor. Ricci tensor is a contract Riemann tensor, and it is the same. It is part of the structure of the famous Einstein tensor. If you want to learn general relativity next time. Okay. Now, how you want to apply all those technique of tensor, especially the most important here is using the Einstein summation convention. Okay, very easy. I mean, it's just it's tedious, but it's easy. Okay. So you know, right? Mu, all alpha, beta, whatever, beta we contract already. Mu, alpha, beta, all running from 0, 1, 2, 3. Okay, 0 already. So that means x alpha is equal to x0, x1, x2, x3. Okay, meaning what? The time is r is beta. So let's say we want to find r22, meaning that we want to find r. 2 is r. 2 is r, right? One is x0 times x1. 2 is theta. X1 is R x2 is theta. So that means R theta theta. Sometimes people you can write this way, but easy to do calculation by using numbers. But this sometimes yeah, the final result you use R theta theta. R theta theta means R2. So you say R11. That means R. So R00. That means R. Let's say for example R theta theta is equal to R. Let's say okay. Never mind. I think just cut here. Nanti you confuse. Okay, R theta theta. You want to find R theta R. So we extend those things first. We can find many things. Usually they have only diagonal part of it. We have which is non-zero. The other one is others is zero. This is the only thing that is. If you let's say for example you put 0, 1, it could be 2, 0, it could be or anything which is non-diagonal. Let's say 2, 3. Mostly you get 0. But this is something that is it has some value. This R dt is R theta theta R P. Okay, now how one. Okay, R we just expand R mu v. R mu we take R mu is equal to this one. Okay, this one is first term. Okay, first term is alpha mu. So which one is the dummy index? The first term. Alpha mu alpha. Which one dummy index? Huh? This one. Which one is the dummy index? Put umbrella. Dummy index, which one? Alpha. New, because ini alpha. Sometimes this one we can write this way. Can write this way. We don't need to put x alpha differential, but we can write this way. That means this is like a covariant. This is like a contravariant. So this is we can contract. I mean this is not we can contract. We cannot contract because this is operation. But this is the what the umbrella ataupun the free index. The dummy index. Okay, dummy index. So which are the dummy index? This one, which one is dummy index? This one alpha. Alpha which one? Alpha is to beta.
Beta equals alpha.
Yeah. This one. This one. This one. Which one is dummy index? Which one is dummy index? So that alpha also right? Alpha also right. This one and this one. Okay. Tapi ada lagi satu. There's one more. Sigma also dummy index. Sigma this one and this one. Sigma also dummy index. This one alpha cross sigma and sigma. So we expand that. Faham?
So the
Okay.
dummy index is the one yang with kedua-dua terms pun ada ke?
Yeah, dummy index where we can expand. I mean 0 0 plus 0 0 plus 1 1 plus 2 2 and so forth. So for example this one, we can expand that one. So okay, I mean I kat sini number sikit. You can write this way DXT X alpha, and then this one is alpha mu. Okay, so mu. Okay, mu. Okay, the first one mu. The first one is 0 0, and then you add 1 0 mu x1 2 Nampak? You can add them together. Okay? You using the unsigned summation convention. 0 0 1 1 plus 2 2 and 3 3. That's what it goes. Okay? Minus satu lagi. Minus this one. Minus this one. Okay, minus this one. This. Minus what? Okay. This alpha mu alpha, and then dx, this one x mu. So minus, tapi this is the dummy index alpha. That means you can differentiate of what is inside here. You can expand. Okay, you can expand this. What's inside? So we mu 0 0, right? Mu alpha, and then mu 1 1, right? Mu 2 2, plus mu 3 3. Nampak? Got it? Nampak? Ada? Nampak? This one. Mu alpha. Mu alpha. So alpha is the dummy index. Okay, mu alpha. So kita expand this thing today. Ini tak ada. This one is just differentiation respect to this thing. But this thing can be expanded. Then be expanded like this. Okay, nampak? You got it? Everybody? Okay, now this one okay, dah habis. Dah settle. The first two settle. No, the second one. Ni agak panjang sikit. Quite long, lengthy. But very fast. But why is lengthy? Sebab dia ada dua dummy index. One is gamma, the other is alpha. So we want to tackle which one first? Anything. So I think we tackle gamma first. Pun okay? Okay, let's see. It's okay, doesn't matter. It's gamma or sigma. Sigma and alpha. Sigma is dummy index, alpha also. This one. Very good. I always look at it. So sigma here, and then this dummy index here. Dummy index here dengan dummy index. So we take the dummy index. So this one is plus sigma mu, and then sigma the dummy index, and then alpha. So we take sigma at sigma 1. And sigma 1 maknanya plus sigma 1. Sigma 1 is 1. 1, and then mu, and then sigma 1. But this thing can be expanded. This one. Okay? So this one is you buat macam hubungan. This one is bracket. This one is sigma, and this thing alpha can be expanded. Now become 0 0 plus 1. So we talk about 1 as a sigma, alpha as 0, and then alpha can be expanded. 1 1 as a sigma, and 2 2. 1 is sigma and 3 3. Of course, you can make. People have already make a program out of it. Mathematica, dalam matematika ada, you can make program of it. Kan? But this I want to show you how the raw calculation of it.
Tak start dengan kosong ke? Kosong.
Itu. Yeah, right on. Start with kosong. Sorry, very good. Very good. Start with kosong. Apa lagi? This one. Mana pula? Sorry. This one is sigma sini. Itulah. Sini is 0. This one is 0. This one is 0. This one is 0. This one is 1. Right, betul time. Okay. Faham? So sigma is start kosong. And then you start again. And then add some more. When sigma is 1. This is right when sigma is 0, when sigma is 1. So see 1 sigma 1. So everything sigma here. When there is 1. Sigma here. Sigma is 1, sigma 1. 1, 1. And then this one can expand. The 1 and then start with 0, 0 plus then 1, 1, 1 plus 1, 2, 2 plus 1, 3, 3. Got it? 0, 1. Let's play. And what is it? Very easy. And number 2, mu. Okay. This is 1, 1, and then 2, 0, 0 plus 2, 1, 1 plus 2, 2, 2 plus 2, 3, 3, and the last one for this term, right? For this term, okay, is, and then 3, and then this one is 3, 0, 0 plus 3, 1, 1 plus 3, 2, 2 plus 3, 3, 3. Okay. Nampak tak? Okay. Itu that kita the third term. Now the fourth term. The fourth term agak pening juga tapi similar to this way sebab dia cross. Ini it cross to alpha which this one. Alpha this one it cross. And then alpha gamma it cross. So you have to be careful. So everything is negative. So kita start everything is negative lah, the whole thing. Tapi dia start negative, but kita buat dalam operation summation. So kita negatifkan dia. Okay, we expand it. Mu alpha. So this one, the gamma is start from 0. Okay, let's say now gamma is 0, 0, 0. Sebab ya 0 and then 0 and then 0 and then 1 0 2 3 0 and then 0 and then kita just plug in mu okay, and then alpha, not alpha, that 0 0. So mu is mu. Okay, bukan mu. Sorry. Okay, sorry. So mu this one. Mu alpha. So alpha ni this one alpha ni with this one. This is mu. This one is mu. And mu this one is mu. All this is mu. Okay. This already free index. New is free index. Mu and nu is free index. Or if you look at this, which is answer, mu and nu is the free index. And the free index could be kan diagonal tadi could be 0, 0 or 1, 1 or 2, 2 or 3, 3, which is non-zero Riemann tensor. But so okay. This one, sigma, sigma, 0, 0, 0, 0, and then mu, check already. And then this one is the cross, really. 0, and then this 1, 1, 2, 2, and then this 3, 3. Okay, and then this is what in the middle. It's mu, right? Mu alpha, mu 0. So this mu 0. Mu is mu 1. This mu 2. This mu 3. Okay. But so this cross, okay, is 0 when sigma. So when sigma is 0, sigma 0, 0, 0, 0, 0. And then alpha cross 0, alpha 0, alpha 1, alpha 2, alpha 3. And we work, this is add together, we work for, and sigma is 1. Sigma is 1, mu 0, 0, okay, sigma 1, mu x is mu sigma 1, then 1, then 1 mu, and 1, 1 mu, mu 2 plus 1 mu 3, and then this is mu 3. Okay, this one. And then the other one, 2 more to go, is 2 mu 0, 0 to mu. Have to be careful, right? Have to be careful to this one is 2. Okay, sigma is 2, mu 2, and mu 1, 1, 2 mu, 1, and plus 2 mu 2, and then 2 mu plus right, 2 mu, 2 mu, and then 3, and then mu. Okay. Remember, mu is the free index. Okay, so easy. Then plus one more 3 mu 0, 0, 3 mu plus 3 mu 1, 1, 3 mu plus 3 mu 2, 2, 3 mu plus 3 mu 3 and 3 mu. Okay, so step the whole Riemann tensor. Very easy, right? So, easy but tedious, right? Easy kan? Tapi dia macam panjang ni. Boleh? Okay? So far okay, super okay. So now kita akan cari R0, contohnya R0. You tak perlu calculate everything. We just okay, kita tengok R00. What happens to R00? So R00 or R22 or R33, choose whatever. R33, R22, whatever. So let's say for example we want to find R22. R22. We just replace what example is R2. This means that it is equal to mu. This means that mu is to 2, mu is equal to 2. So you just replace the new to 2, mu to also 2. Just replace that. Then you tengok what happened. Okay? Just replace. Okay, just replace. So for example, so want to find R2. Usually R22 is sometimes R22 also people call it as R 2 R theta theta. R1 R11 R00 called R33 called R33. Same thing. And sometimes people call, people just write it down like this, R20 and some 3, 2, and then let's say sometimes people call like this theta theta, and then theta, and then they call t theta, and this one big T, that means T contract with T become R theta theta. So you don't need to think about this T. You don't need to worry, it's already contracted. So if what length is R theta theta or R to 2. Okay? So it doesn't matter what indices here in the middle. Doesn't matter. Doesn't matter. What the contract with. Sometimes you just what is R T R T T R T R. Okay. You don't need to derive the whole thing back. Don't need. Because this thing is already contracted, so you can get just concentrate with it. And sometimes if using TT is very difficult. Keliru kan, keliru. Lepas T apa lah. So better we change it to numeral number. So T is 0 0. So senang. 0 after 0, 1, 2, and 3. Either we have to repeat T after T, of course R, the R theta, the theta is T. So better sometimes we work inside, we work using number instead of T. Okay. Okay, I give you some example. There's some portion of calculation. Let's say R22. We see the calculate A1 to calculate R2. So the first one, what you call the first term, the first term is that di atas sekali. Okay, but you know, it's not difficult because of what? Not everything of Christopher symbol second kind, this one, has value. Most of them are zeros, so you can cancel it out. Okay, I show you get one example. Okay, let's take okay. Now R22, you just have to replace the first. Now kita buat kita ambil the first term kat kami. The second term is third term, to fourth term. Okay, panjanglah third term dengan fourth term dia panjang. But it's very easy. Okay, the first term this one. I mean R00, R22, you just replace new mu with 22. Okay, so what we have? So X, it is the first term. Okay? The second term maybe kita buat kalau sempat lagi kan, kalau tempat lagi kita buat everything. But ada cerita tempat. Okay, 0, 0, 0, new mu 0, 0, and then X some more, X 1, and then 1 0, 0, 0 pula, 2 lah. Sorry, 2. Okay, always petang kan. Okay, 2. 1 plus the other one is 2, 2. The X 2. 1 X2. Okay, the last one. And 3, 2, 2. mu mu 2 and then the x3. So we have to calculate lah everything, but don't need to panic. We have four term to calculate kan. But actually for example for this metric kan, this one I nak okay, boleh erase this one. For the metric that I have, I could give you, for example, your take-home quiz, I could give you some other metric, yes. But this one, this example, I give you metric inside it. Maybe for take-home quiz, I will give you the metric of black hole, maybe, or metric of wormhole. Okay. So the metric E to so for the metric of this one is the metric E. Okay, this metric. So we have this metric. This is you can find it. I think you can try to. It's a very good book by Paul Dirac. Have you ever heard Paul Dirac? Yeah, Dirac delta everything. Good. Paul Dirac. It was he taught general relativity also, but he's famous with antimatter. He derived the equation for antimatter. He derived the equation purely mathematical basis. From nothing, he derives. He's like combining general relativity, special relativity with quantum mechanics. Quantum mechanics plus special relativity. Quantum mechanics plus general relativity is very difficult. Up until now, people haven't found the. But general relativity with special relativity, we call relativistic quantum mechanics. Relativistic quantum mechanics is one of the pioneers is Dirac. So during his work on the relativistic quantum mechanics, he found the equation for antimatter. You love antimatter, okay? It's not science fiction, it's being used already. Antimatter is being used already. No more science fiction. Last time it was in as an antimatter torpedo, like in Star Trek kan.
I saw the article where they found that antimatter makes a lot of gravity.
Yeah. Okay. This is matrix, very easy matrix. This is what is the simplest matrix. From this matrix, this is what we have. This is G mu, G00, G0, E to V. This V or V is a function of R. Lambda is a function of R. And so G11 is negative E to lambda. Okay, G22 is negative R squared. G33 is negative R sine theta. Okay, sine squared theta. Okay. Now from this I could give you calculation also. I think this one I showed last week. Okay? You can calculate the Christopher symbol second time. Let's say you want to calculate this one, alpha, beta, gamma. How you want to calculate this is you can contract with this. You take a metric alpha, and then you contract with mu which is and then this is first kind Christopher symbol, beta, gamma. So, mu, beta, gamma. Mu contracted. What left is beta, gamma, and alpha here. And but this one is G alpha mu over 2. Then you, I think last week I did this one last week. beta, and then G mu gamma plus G x gamma G mu beta minus it all has pattern. Gamma is, maybe if you can look, you can see the pattern. The mu. Mu, the last term, this one is G beta gamma. Okay. From this you expand similar to do expansion of by using unsigned summation convention, you get this one. Which is non-zero. More 8, ada 8. 8 terms which is non-zero. Others is 0. But I show you what they all mean. So last time I calculate half lambda prime kan. That was because I didn't put 2 here. This new. That's why it's different. But almost same. So it doesn't have lambda. So okay. 1 to 2 is equal to negative RE, negative 2 lambda, and then 133 is equal to negative R sine theta E, negative 2 lambda, and then you don't need to copy this one. I will if I give you, but never mind if you want to copy it, okay. But actually I will for quiz or anything, I will give you every important resource table. But yeah, maybe you have to calculate this resource table. But of course, if you want to calculate, it's very lengthy. I show you why. Because not all resource table have value. It's good in some sense because you don't need to know everything. You just concentrate on the thing that has value. Because you can imagine this crucible to be many. It's like, so you have 3 and you have what? 8. 1, 2. You have, okay. With each of these 0, 1, okay. Alpha, mu, beta. Each of these have four types, four things. I mean, could be 0, could be 1, could be 2, could be 3, right? Each of these have 4. So 4, okay. It's like, okay. Let's see, for example, mu beta. This one mu 0 mu okay, 2 4 1 8 1 2 mu beta, then 3 mu beta, and then each of these will be okay. This one saja will be 0 beta, and then 0 1 beta. It could be 0 2 beta, could be 0 3 beta, could be and so forth. And then each of these is 0 0 1 0 0 and 0 0 0 1 and 0 0 2 and 0 0 3, and each of these also like that. So could be many. The first time you calculate this, of course, you want to make sure which one is 0, which one is going to be very lengthy, very lengthy. But if you involve in general relativity, like you have to study everything. But of course, in like if you do exercise, you will be given all the non-zero terms. So the other terms, there could be many terms, right? Each of these have space and time with term, right? So could be many other terms, but those other terms is 0. So only this that is non-zero. So for example, we want to calculate this one, or this one. Okay. The first term of reversible. The first term of reversible. So we want to calculate the first term of reversible is 1. So we want to calculate 2 2. Okay. So you find out whether if this one is zero, just concentrate which is non-zero. So 0 to 2, does 0 to 2 exist? 0 to 2, nothing. Very easy. Cancel. 1 to 2 exist? 1 to 2. Ada sini. So tengok. Okay. 2 to 2 ada. 2 to 2. Nothing. Okay tak? Oh, cancel. 3 to 2. 3 to 2 ada. Tak juga. Nothing. There's nothing. Okay. So you just have to concentrate. Easy. Kan? Easy? Nampak? Everybody? Okay. Easy? Kan? Tak ada. Dia tak boleh dekat sini. Just only ini saja yang non-zero. Yang ada value, yang kita boleh operate. Others like this one, like 0 to 2. If we calculate 0 to 2, it be 0. If we calculate crystal symbol 2 to 2, we should get answer of 0. 3 to 2, 0. So what exists here? Of course, the first time you do the crystal symbol will be very likely. Okay? But never mind, for exercise or use this mathematical physics exercise, it's just I will give you the non-zero one. Okay? Okay, now what we want, how we just differentiate this one. So differentiate. So okay, I'll give you an example of differentiating this one. Erase it, okay. Okay. So I'm going to differentiate 1, 2. Okay. Let's stop at. Okay, this one is 1. So 1 to 2 differentiate with respect to x1. So 1 to 2 is what? 1 to 2 is this one. 1 to 2 is negative RE negative 2 lambda. Negative R. Okay, with respect to x1. x1 is what? R juga. Okay. This one is R. You make XR. X1 is R. X1 is R. X0 is T, X1 is R, X2 is theta, X3 is P. Therefore, spherical coordinate. So we don't use Cartesian coordinate. It's impossible to use Cartesian coordinate in general. Okay. So we can just differentiate this thing. Okay. First, we're going to differentiate very easy. Negative R, take out negative. Take out negative. So we differentiate negative dr, dr, and then E, negative 2 lambda, okay, and then plus R, and then D, E, negative 2 lambda over dr. Okay. Okay, this one is very easy to differentiate. We got negative 1 already, negative E, 2 lambda, this one. R, using the, always use this, or the negative 2 lambda, right? Negative 2 lambda, if R. If, so we have negative E, negative 2 lambda, R, E, negative 2 lambda, and then negative 2 have negative E 2 lambda plus R E negative 2 lambda. This one is negative negative is positive, positive, negative, negative positive is 2 R E 2 lambda, and then lambda prime. Lambda prime is 2 lambda. So we have this. So this is the equation. This is the equation of this thing. Of this first term. Then you tackle second term. Very easy. Okay. We do already. So you want to stop here or you want to continue another 5 minutes or anything? Okay. Letih ya. Okay. Alright. So just similar kind of calculation for this state. Okay. The first one is what? The first one is we calculate this thing, right? Calculate this thing, so we can do this one. 1 to 2 ada. And then the second one also ada. So you replace with mu, and mu will replace with 1, right? 2 with 2. So this what I give you just once more. There's another example of calculation. Okay, just replace. No, we have already. This term already we calculate already. We got that one. Or this one is okay. No, just replace mu and mu is 2 and 2. So what we have is negative 2 is x2, and then 0, 2, 0 plus 1, 2, 1 plus 2, 2, 2 plus 3, 2, 3. Okay? Okay. Now kita tengok what is there here. Okay. 0 to 0 ada? Nothing. 1 to 1 ada? 1 to 1 ada? Tak ada. Right? Ada. 2 to 2 ada? 2 to 2 tak ada? Tak ada semua. Semua tak ada. So di setengah dulu kan? 3 to 2 to 3 ada? 3 to 3 ada this one? Cotangent. So cotangent only. Okay. So negative the R the cotangent. 2 to 2 tak ada? 2 to 2 there's no 2 to 2. Okay. 1 to 1 ada? Mana ada? Tak ada juga tadi. 2 1 2 ada. Okey. Tangent cotangent theta. Cotangent theta. Now we differentiate with what? X2 x theta, right?
Ya.
Tadi kita differentiate apa tadi? X1 kan? R. Yang atas tu. So R. R. Okay. Now we differentiate with theta. With X2. Okay, you letih. A lot of calculation, but slow and you study. Okay, cotangent. What will we get? Cosecant? Cosecant, right? Cosecant theta. Never mind. Relation with respect to theta, you know, tangent is 1 over tangent. Jadi cos theta over sin theta. 1 over cotangent is 1 over tangent, so just differentiate this thing. Okay. One is sin theta, then d cos theta, d theta minus cos theta, d sin theta, okay, and then over theta, and then sin squared. So you got negative, and this one is calculus je, just Sin square cos square jadi 1 over sin ganda 2 theta jadi cosecant square theta. Okay. That's it. Then just the second term. Second term already. Now just calculate the third term and then fourth term. The term is quite easy. Just one fourth term. First one is very. Okay. You okay? Okay, then that's it. That's it for today. So I tak nak this one to be my last. So maybe we have another one last. Tapi itu tak masuk dalam exam, tak masuk dalam apa? Tak masuk dalam dalam quiz ke apa ke? This one ada dalam tengok quiz nanti you tengok. So you betul. Kalau tak faham datang office So the we have another one class extra. Maybe after Chinese New Year, tapi that topic tak masuk dalam apa, tapi it is very important that topic. You have to know Lagrangian. So I'm going to talk to you Lagrangian. Maybe you take 1.5 hour class, just start from 5:30 to 7. Right, 5:30 to 7. Okay. So it was a very good topic lah. Being a physicist, you must know Lagrangian. I will take from that. Maybe I will tell later when we will do this.